We're almost halfway through our video series. Last time we investigated the mechanism further. In this episode you will be introduced to the field of archaeoastronomy. After that you will once and for all know what the difference between a lunar eclipse and a solar eclipse is. And as promised at the end of last episode, you will learn how CAD works. The most famous ancient calendar is probably the Maya calendar.
The one that predicted the end of the world in 2012?
Well, yes and no. It's actually composed of three simultaneous calendars. The long count, which supposedly predicted the 2012 phenomenon, is 2,880,000 days long. The Maya believed the universe gets destroyed and regenerated after each cycle. Then the Tzolk'in, a divine calendar of 260 days with 20 periods of 13 days, possibly based on the cycle of Venus or on the duration of a pregnancy. And the Hab, a civil calendar based on the 365-day solar calendar, divided into 18 months of 20 days each, and a 5 days long bad luck period. The observation that a year is about 365 days long is one of the earliest recorded astronomical cycles. Megalithic monuments such as Stonehenge were used for timekeeping, but there is also examples from the other side of the world, notably the Wurdi Yuang stone arrangements by Australian Aboriginals. This is what the discipline of archaeoastronomy addresses: how our earliest ancestors understood the sky.
In ancient Greece, it was more common to use solar calendars. Developed in Babylon, the Metonic cycle is a period of 19 years, which also corresponds to the time after which the moon phases reoccur on the same day of the year.
This cycle is used in the Antikythera mechanism on the upper back dial. We've already seen how the Egyptian calendar influenced the making of the mechanism. With this second example, we can see how ancient Greek knowledge is inspired by earlier discoveries of their neighbors around the Mediterranean. Still, the Greek astronomer Callippus pushed the understanding of time further by understanding that a year is closer to 365.25 days. By quadrupling the Metonic cycle, he obtained a time period with an integer number of days to compute the moon phases, 76 years.
The Metonic and Calippic cycles can be used to compute when an eclipse will occur. Let's see how in our astronomy section. The word eclipse alludes to the obscuring of an astronomical object by another object passing in front of it, so that a viewer cannot see it anymore. The alignment of three objects is referred to as syzygy.
In the Earth-Moon-Sun system, us terrestrial observers can observe two phenomena, solar and lunar eclipses. A solar eclipse is when the moon passes in front of the sun. During a total solar eclipse, we can see the sun being totally hidden by the moon. Obviously, the moon is much smaller than the sun, but its proximity to us means it can appear to cover all of the sun's surface.
Fun fact: the moon is slowly spiraling away from Earth at about 3.8 centimeters per year, which means that in 600 million years we won't be able to observe total solar eclipses anymore.
What still will be visible is the moon's transit in front of the sun, but since it won't cover the sun fully, it will be an annular eclipse. On the other hand, a lunar eclipse is when a full moon enters the Earth's shadow.
You may be familiar with the expression blood moon. That designates the reddish color that it takes when the eclipse is total.
This is due to a phenomenon known as Rayleigh scattering. It occurs because particles in the Earth's atmosphere disperse photons depending on their wavelength. The only light that reaches the moon, and which it then reflects back to us, has higher wavelengths, i.e. it appears red.
As the Earth's shadow is still pretty large when it reaches the moon, lunar eclipses can be observed for longer than solar eclipses. And in one night, it will be visible from many different locations.
You may think that these are totally random occurrences.
Or you might think that they happen too rarely in one place to have been noticed as regular events during antiquity.
But we have already seen that ancient Greeks were aware of the Metonic cycle and later the Ecliptic cycle. The best-known eclipse cycle, though, is the Saros, which corresponds to 223 lunar or synodic months, about 18 years. The Metonic cycle has 235 synodic months, which, as we discussed earlier, is about 19 years.
Why this rather large difference? Surely they can't predict the same thing?
Well, both cycles are imprecise in the sense that they actually contain non-integer numbers of days. This means that each time after a cycle duration, the best place to view the eclipse will have shifted to a different location on Earth. That's why the Ecliptic cycle is useful, as that one contains an integer number of days.
To assume the duration between two eclipses is the time it takes for the syzygy to be almost exactly the same again. The Saros and Metonic cycles are approximations of that, and the Ecliptic cycle is more precise.
Interestingly, these cycles work for both solar and lunar eclipses. Now that you're over the moon because you know the difference between lunar and solar eclipses, and more, let's take a look at a tool we use for modeling the cycles as in the Antikythera mechanism. Computer-aided design can be defined as the use of computers to assist engineers in the creation, modification, analysis, or optimization of a design.
Working with CAD allows engineers to easily and quickly visualize designs, parts, or assemblies, as well as doing calculations and automatically generating the bill of materials, which can be thought of as a list of the components with details such as cost.
In some cases, one CAD file can replace over 200 engineering drawings. Imagine all the time saved. It also allows for components to be edited easily and quickly.
One of the most useful applications of CAD is that it allows for complex calculations to take place in a short period of time. For example, in fluid dynamics, structural analysis, heat transfer, and many more.
The program used for this project is called Kata V5.
In this crash course, we'll show you how we make one of the gears for our mechanism. So this program that you're looking at is Kata V5, which is widely used in mechanical engineering. The first step is to make the blank gear without any of the teeth on it. So to do that, we just make a big circle with a small circle inside of it. And so we can quickly do the drawing. And then when the drawing is done, we only have to do a pad. A pad basically gives the drawing a substance in one of the directions. Good practice when you're doing one of these projects is to always name whatever you're doing. So here we just quickly renamed it gear without teeth. Now I'm just gonna draw a profile of one of the teeth. I already have the calculations for this, so I just plug in the numbers and quickly do the drawing. Again, with this drawing, we're gonna pad it like we did with the last one to give it substance and make it 3D objects. So now we quickly rename this single tooth profile because, as I said, it's important to have good practice with this stuff. Now what we're gonna do is a circular pattern. So we're gonna repeat the single tooth profile and make it a complete crown around the whole gear. And basically it's a 64 teeth gear, so we're gonna do it 640. The last step is doing the sketch and pad for the hub, which is a piece that prevents the gear from moving horizontally on the shaft. Here you can see the finished mechanism, and I'm going to show you how the gear that we just created integrates into that design. Gear is the B2 gear, and it lies in the moon train, as you can see.
We've seen that calendars are an extremely handy legacy of ancient cultures to study their perception of the cosmos, and how eclipses can be mathematically described. Aspiring engineers, you now know how to get started on using Kata V5. Next time, we will look at the ancient Greek undertakings in astrology, then learn more about our natural satellite, the moon, to finish off by examining the incredibly accurate way the moon was modeled in the Antikythera mechanism.